Hi, everyone. I'd like to take this opportunity to welcome you all to our last seminar for our fall 2023 series. Our seminar series here at the Big Data AI Hub aim to connect researchers, industry professionals, and students to engage in discussions about recent developments and challenges in the field of big data and artificial intelligence. By promoting dialogue and collaboration amongst these groups, the seminar series contribute to the advancement of knowledge and the acceleration of progress in the fields of big data and AI, addressing critical challenges and pushing the boundaries of what is possible. These technologies have the potential to enhance decision-making, drive efficiency, improve quality of life, and address some of the most pressing challenges facing society today. In today's session, we are focused on applications related to climate change. Big data and AI enable the analysis of large data sets from satellites, weather stations, and environmental sensors to make predictions about climate patterns, extreme weather events, and their impact. This information is essential for developing strategies to mitigate and adapt to climate change. With that said, it gives me great pleasure to introduce our speaker, David Rolnick, an assistant professor and Canadian Institute for Advanced Research AI chair in the School of Computer Science at McGill University. David is a visionary leader who has made significant contributions to the fields of machine learning and climate change. In addition to his academic roles, David is the co-founder and chair of Climate Change AI, a nonprofit organization dedicated to driving impactful initiatives at the intersection of machine learning and climate change. David also serves as the scientific co-director of sustainability in the digital age. In 2021, he was named to the 35 Innovators Under 35 list by MIT Technology Review, recognizing his outstanding work in machine learning and its vital role in addressing climate change. Please join me in welcoming David, whose dedication and expertise are making a significant impact on our world. David, we really look forward to your presentation, and thank you from all of us.
Thank you so much for that very kind introduction, and it's a pleasure to be here. This is a nice long period for a talk, and I want to start out by saying that since we do have this time, I would really welcome questions and comments throughout in the chat. So please feel free to post in the chat if you have a question that comes up. Then we should also have time for Q&A at the end, but this can be a little bit more of a discussion, even though we obviously are in a virtual medium. I will kick off with some quick background, because I realize not everybody is coming in from the same background here. In particular, background on climate change. I don't think the topic of climate change needs very much introduction, but maybe framing from where we are coming. Climate change is increasingly present around us. We're seeing its effects becoming both more frequent and more severe. And it's important to remember that climate change has a disproportionate impact on already disadvantaged communities and typically serves to reinforce existing societal inequities, both in regards to where geographically the impacts of climate change are felt, which are often in those regions and countries that have actually done the least to contribute to it, and also in the context of communities within a geography. Often those communities which are already at risk get hit even harder by the impacts of climate change related hazards. I'm often asked, given how significant and severe climate change is getting, is it too late? Should we just give up? Or alternatively, should we leave action to the space of policy? And my response is that climate change is not an on-off switch. How bad it gets depends on what we do now. There are many people who have died as a result of climate change, and many more who will die regardless of what we do. But we have it in our power to decide whether it is going to be more or less of a catastrophe. And there are all kinds of action which are necessary from within the technology space as well as from within the policy space. And it's kind of an all hands on deck problem. We need net zero greenhouse gas emissions by 2050, according to the UN's Intergovernmental Panel on Climate Change. And we are nowhere close to achieving that. Even if all countries were to follow through on their commitments in the Paris Accords, which they are not on pace for doing, we would still be falling far short. So there is huge room for action. And there are several kinds of action which are needed. Mitigation, which is reducing greenhouse gas emissions, but also adaptation, which is resilience to the consequences of climate change, given that those consequences are that some consequences are inevitable and other consequences are a question of degree. There is also climate science, which is sometimes lumped in with adaptation, which refers to understanding the Earth's climate and how it is changing. So if you think about people, if you see people using the terms mitigation, adaptation, and climate science, that's what they're referring to. Now, what are AI and machine learning? I realize this is a seminar series on AI, so many are coming from an AI background, but just so we're all on the same page, let's talk through what AI actually means. According to the OECD, AI just means any computer algorithm that makes predictions, recommendations, or decisions on the basis of a defined set of objectives. Now, you'll notice that's extremely broad. It encompasses many things which are in the news as AI, but also many things that aren't, which would be considered to be very low tech. Within AI, there are a couple of different families of approach. The approach that people generally mean nowadays when they talk about AI is machine learning, and that refers to AI algorithms that infer patterns from data. You give the algorithm a large amount of data, and it picks out patterns which are useful in solving the problem that you have posed. Such approaches have become both extremely powerful and extremely popular recently, thanks in particular to deep learning, which is also called neural networks-based approaches. However, it's worth noting that there is machine learning, which is not deep learning, and that those algorithms are quite effective. There is also AI, which is not machine learning, so-called symbolic approaches for AI, and approaches that fuse the symbolic and machine learning-based approaches. So these are big, happy families of algorithms, and they encompass quite a lot. And in particular, they are not just the algorithms that you hear about on the news. Most of AI and most of machine learning, for example, is not GPT, which I will talk about a little bit at the end, but which doesn't actually come up very much in the climate space. Some strengths of AI and in particular machine learning-based approaches. Machine learning is very good at performing straightforward tasks quickly and automatically. If there is a task which a human might not have patience to perform at scale, that can, in some cases, be a task that machine learning can scale up. Finding subtle patterns in large data sets. Since machine learning approaches work by finding patterns and picking out the relevant patterns necessary for making a particular kind of prediction or decision, finding patterns is something that they excel at, potentially more subtle patterns than a human could pick up on. And optimizing complex systems. If one has a system with many knobs that can be turned, a human might not have patience to explore all of those, might not have time. A machine learning algorithm can be good at working out the best way to optimize that system. We'll see examples of this in the climate context in just a few minutes. Some weaknesses. Since machine learning algorithms are fundamentally reliant upon data, they are very sensitive to that data. If the data is bad, incorrect, or if it's biased. So for example, if it comes from a restricted geography, or it comes only from certain kinds of equipment, certain kinds of people, then the algorithm will be overfit to those particular regimes, will not necessarily be able to perform in other kinds of contexts. A famous example was a machine learning algorithm designed to solve a video game. If you changed the background color, then the algorithm would completely fail. Clearly, a human would not have such a failure, but machine learning algorithms fit to data, and they don't fit to data in the way that a human would do. Machine learning algorithms also can't think outside the box. They are designed to interpolate. They're not designed to extrapolate. They pick out patterns within the data that they've seen. They don't have a notion of creativity or a broader world model that allows them to make insights that a human would make. It is very easy to confuse extremely good pattern matching skills with ability to be creative. And there are many arguments on the topic, but really the notion of thinking outside the box is something which is so far outside the scope of our algorithm. And then generally, explainability and interpretability are very limited. It is sometimes possible to work out what contributed to a particular decision or output of a machine learning algorithm, but generally speaking, these algorithms are quite opaque about what goes into making a decision or an output. This is an area of active work. All of these are areas of active work in the space of machine learning research, but these are typical strengths and weaknesses to bear in mind for most algorithms. So I'd like to talk through, first of all, what we see as the space of machine learning as it relates to climate change. Why are these two seemingly disparate areas related? What opportunities are there for AI and machine learning in the space of climate action? And I'll talk about some overall themes. These are themes which are covered in more detail in this overview paper called Tackling Climate Change with Machine Learning. I encourage you to check it out if you're interested in more detail or in an exhaustive overview, 100 pages of detail on what applications specifically machine learning can be useful for. But I will talk about some overall themes which come up across these many different areas. It is worth remembering, climate change is not just one problem. It's not just one area. It encompasses many, many different sectors, everything from electricity systems to buildings to transportation, heavy industry, so it's like steel and cement manufacture, agriculture, forestry, these many different areas. But across these different areas, we do see some overarching themes. The first theme is in improving operational efficiency. So taking some system that is often already automated, but is not controlled with maximal efficiency. For example, heating and cooling systems in buildings generally have very simple controllers, and it's actually scope to make them much more efficient with more sophisticated AI-based controllers. HVAC systems refers to heating and air conditioning systems in buildings. These are already, AI-based systems are already in use in smart thermostats for personal homes, but the problem gets much more complicated if you're working with a larger building, like commercial or industrial setting. And we're increasingly seeing AI-based controllers in these buildings, but it's an area where there is huge potential for increasing impact, even as we're seeing very promising work being done by companies across this space. I would also note that in the space of manufacturing, there is huge potential as well. Oftentimes, so-called difficult to decarbonize industries actually have the most potential for efficiency increases using automated AI-based controllers. Steel and cement manufacture together contribute about 15% of global greenhouse gas emissions. So even a slight percentage improvement in efficiency can be really effective. Gathering information, taking large unstructured data sets and parsing them to give useful information. Oftentimes, such problems involve satellite imagery, which is one of the biggest sources of really unprocessed raw data available. But it can be used across many different application domains, from tracking carbon stock, so how much carbon is stored in a piece of land to help shape land use decisions, understanding where deforestation is happening in real time, tracking flood risk, understanding where communities are at risk from coastal flooding, etc. And this can sometimes also be useful in parsing big corpora of natural language, so like financial disclosures, finding climate relevant pieces in corporate financial disclosures. Forecasting is the third theme that we see here. So a couple examples here are in the electrical grid, where it's really necessary to ensure that the amount of power available meets the demand for that power at every given point. And so here, forecasting the supply of electrical power, since that varies, especially with solar and wind power, where the sun and the wind can vary from moment to moment, forecasting the amount of power available and also predicting the demand for electrical power, making sure that these two are matched. That can be essential in not overproducing power, so not wasting electricity, but also in ensuring that you can integrate solar and wind farms into electrical grids by making sure that they are maximally utilized and are not underproducing. These things are often done manually historically. For example, I know that in the UK, people running the electrical grid used to have a timetable of television shows. And they would know that whenever a particularly popular program ended, there would be a 10% bump in electricity use as everybody got up and went to make a cup of tea. Seriously, this actually happens across the UK. There's a noticeable bump whenever everybody turns on their electric kettles at once. So this is some of the challenge in predicting electricity demand. But the UK's national grid recently introduced new AI-based forecasting systems that actually cut the error rate in half for predicting electricity demand. Speeding up simulations. There are many situations where we want to have a simulation of some complex physical system, like the climate or weather or electrical grids. And in these cases, our physics-based models have historically been used, and they're very good. We understand the physics of the climate and the weather very well. However, these can be very slow. It can take months to run a climate simulation, even on a supercomputer. And so having faster approximate simulations using AI can be really relevant. We'll get into more examples. And then final theme I want to touch on is accelerating scientific discovery. For example, there are many situations where we would like to innovate to drive climate tech forward, and just doing all the experiments is a major bottleneck. So AI can help suggest useful new experiments on the basis of which experiments were successful in the past. In these cases, for example, we could see AI being used for helping design new batteries, new solar perovskites for use in solar cells, and new materials for carbon capture, and so on. I'll get into examples in more detail from my own group in just a moment, but I do want to ask if there are any questions at this stage. These examples that I've touched on, I also want to emphasize, they are all being used. AI is being used in these applications right now, with the exception of scientific discovery, which is much more longer term in its horizon. These are already in operation, having real impact at TRL 7 or above across the world. Okay. Yes, for this last point, pharma is a big space as well. Scientific discovery is used. Accelerating scientific discovery is a major area of application for machine learning in drug discovery. Okay, so let's go into some more in-depth applications, examples from within my own group at Mila. Under the heading of improving operational efficiency, a major problem that is faced in managing electrical grids is this problem called AC optimal power flow. It's an optimization problem to try to determine how much power you need to produce at every generator within a power grid in order to meet demand. So you have some power grid that's known, and you have some generators which can produce a certain amount of power each. This is a non-convex optimization problem, which for the computer scientists in the room, you will know that that means that it's hard. It is not possible to solve non-convex optimization problems typically very fast. This is a quadratic but non-convex optimization problem. These, you can see the exact formulation of the problem here. These are complex numbers. Since it's non-convex, exact solutions take too long. And so typically what's been done is that electrical grid operators have simplified the problem. They've actually linearized this problem, which again, for the computer scientists, you know that is a very, very severe simplification, which changes the problem dramatically. And because the problem is simplified, if you solve the simplified problem, you actually don't get the right answer, and you end up wasting electrical power. This is especially the case with solar and wind power. And that's because with solar and wind, the amount available to produce changes from moment to moment, and so you have to solve the problem more frequently. Now, why don't you just throw AI at this problem? Well, naive approaches for using AI, deep learning-based approaches specifically to solve this problem are not very good. They can approximately solve the problem, but they also approximately satisfy these constraints. And in an optimization problem, there are two pieces. There's the maximization or minimization of the quantity you want, and then there's the constraints, which are the things that you need to make sure always get satisfied. And Deep learning algorithms are very good at optimization, but they're very poor at satisfying constraints. They typically trade off between optimizing this quantity and satisfying the constraints. And in this case, the constraints are fundamental limitations on how power flows within an electrical grid. They are governed by system physics and engineering constraints. And so if you violate the constraints, you actually cause a blackout across the system, and the entire grid goes down and people die. So nobody would ever want to use a deep learning-based system that could even potentially violate constraints. So nobody uses AI in this context. We've shown that it's actually possible to fuse the engineering physics-based constraints of the electrical grid with deep learning-based approaches and ensure that we can both optimize the problem approximately and also satisfy these restrictions. We can thereby solve AC optimal power flow problems orders of magnitude faster than traditional methods while not running the risk of a blackout. These methods are actually general for solving non-convex optimization problems, and we anticipate them being useful in many other fields as well. The next set of examples that I want to touch on are in gathering information. So taking big unstructured data sets and turning them into useful information to guide policy or other kinds of decisions. And we're going to talk about ecosystems. So ecosystems worldwide are collapsing as a result of climate change, as well as other factors. And the biodiversity crisis and the climate crisis are really connected. Each one is contributing to the other. However, we don't have very much data on biodiversity. That's because evaluating it takes time. It needs specialized expertise. There is a big world out there, and there are a lot of creatures in it. And so actually understanding ecosystems is extremely hard. Gathering that data is typically very patchy. Certain geographies are more represented than others, in particular the global north. Certain organisms are better represented than others. Birds get more attention than beetles, even though there are 50 times as many species of beetles. AI can scale up ecological monitoring across different geographies, across different taxonomic groups. And we see this really as the future of working in tandem between technology and biodiversity. In our first project in this space, we're developing automated sensors to monitor insects. These are already deployed across 3 continents and in partnership with a network of different ecology organizations, like the Montreal Insectarium, the e-Butterfly Project, UK Center for Ecology and Hydrology, and many more. This is what the hardware for our systems looks like. It's a solar-powered device that can attract insects using a UV light and photographs them using an automated camera connected to a Raspberry Pi. Our AI algorithms identify these insects. We're currently focusing on moths, which represent about 1/5 of all insects and 1/10 of all species on Earth. This data then is sent to experts for interpretation and proofreading. It's providing tools for the ecologists. It's not replacing them. It's giving them more tools to do their job. And this is what it looks like. This is a real output from our system on data from, in this case, Vermont in the US, where you can see a large number of insects attracted, filters out all the insects that aren't moths, finds the moths, puts boxes around them, and identifies them to species with a certain confidence. The rare or interesting moths are then sent to experts for particular review, and this can gather thousands of photos in a given night. We just came back from Panama. We were testing them at scale in the rainforest, and we've actually been using these systems to help uncover new species undescribed by science. The next project in this space that we work on is in fusing together traditional biodiversity monitoring systems with remote sensing, satellite imagery. So here the problem is that, as I noted before, we are trying to gather data equitably across the world, but there aren't people equally distributed across the world. One approach is to set up these automated systems, which you can put out in the field and leave for months at a time and come back and get data from. Another approach is to use satellite imagery to fill in the gaps, because we have satellite imagery for the entire world. And so what we're doing here is we're using the places where we have got data on the ground, plus satellite imagery, which is available everywhere. And we're inferring the abundance of species and certain key ecosystem properties in places where we don't have on-the-ground monitoring. So here, for example, is a particular species of bird called the bobolink. It's found in Canada, and these are some Canadian forests and fields. And this is where the bird has been seen. Birds typically are very well monitored in Canada, but not in all other places. And they're typically actually monitored only in the south of Canada, not in the north. But here you can see that this bird is only found in fields. And it's actually, if you look a little bit more closely, you can see that it's actually found only in fields of a certain age. It's found in hay fields that have grown to a particular height of grass. This is a property which can be worked out by an AI algorithm. And so we can actually predict the abundance of this bird without necessarily going out always into the field. It's never going to be as accurate as field monitoring, but it's a great way to scale up data collection in places where we don't have enough people on the ground. We're also developing algorithms to infer tree species, crown size, other properties from satellite and drone imagery in collaboration with plant biologists in this case. And we're using this to help evaluate the effectiveness of different forestry policies in Canada and elsewhere. I also want to highlight that we actually just launched a global center on AI and biodiversity, thanks to a $10 million grant from NSF in the US and NSERC in Canada, which brings together communities of ecologists on one side and computer scientists on the other to help collect data using AI systems and understand that data at scale, really addressing these bottlenecks in terms of data collection and parsing. The third theme that I wanted to touch on is, again, forecasting. So here we have the problem of understanding what is going to happen based upon time series, based upon data from past time points. And I'd like to touch on the example of forecasting crop yield. So this is an essential problem, given that climate change is leading to extreme weather that threatens food security. We're seeing increasing droughts and drought-induced famine, as well as flooding that also can catastrophically impact agriculture. And governments around the world are really desperate for solutions to understand how climate change is affecting their agricultural production and what kinds of interventions they can use. So we're working together with partners from NASA Harvest, who work with governments around the world to predict crop yield and other agricultural properties from satellite imagery, which is available worldwide again. And we're working with data that looks like this, where we have often smallholder farms, a patchwork of lots of different crops, and we're trying to work out what the crops are and how much yield is going to be produced so that the governments involved can actually step up interventions, potentially give aid, or shape other agricultural policies. The challenge here is that, again, AI needs labeled data. It needs a large amount of data generally, and data can be scarce and uneven across different locations since it relies upon people going out into the field and actually giving information on what crops are where and how much yield they're producing. Here you can see data from our partners at NASA Harvest, where the orange data points, which are information about what crop is present there, they're so unevenly distributed around the world. We have enormous gaps in large places. And we'd like to be able to fill in these gaps. We'd like to be able to use AI, even in places where there isn't labeled data, where there haven't been people on the ground saying, this is what it looks like. This is what you should be predicting. And so we develop what are called meta-learning algorithms for crop yield prediction that can quickly adapt to new locations and crops. So if they've seen coffee in Kenya and maize in Brazil, they can adapt to maize in Kenya or coffee in Brazil. And the idea is, again, that we can actually build in information about geography and, in this case, crop type in order to enhance performance. I'm not going to get into the full details of this, but this is a way to integrate this kind of task-specific information so that you end up with a much more effective set of algorithms that, in this case, can actually generalize to a new location having seen no data on that location. These methods have, again, proven relevant not just in this particular domain, but actually across many different applications, like in optimizing heating and cooling systems in buildings, where we've worked with Brainbox AI, a Montreal-based company, and in monitoring carbon flux, where there are stations of sensors set up around the world, but since there are enormous gaps in the sensor network, we'd like to be able to predict what is going to be measured in different locations, and do so in a geography-aware way. The next theme that I want to touch on is speeding up simulations. And here there's a major gap in terms of climate models. Climate models or simulations are very accurate, but as I mentioned before, they can be extremely slow. And this makes it harder, in particular, to get the localized predictions that many communities need to make decisions about climate change. If you're a mayor or a municipal government, how are you going to guide your response to climate change if you don't know what is going to happen to your particular region, very narrowly defined? And this is important because climate change affects places very differently. You can see that the impacts of climate change are sorry, I think this is not climate change. This is actually global temperature. So I take this back. But if you were to look at a map of how climate change impacts different regions, you would see that there are many different hotspots. So for example, the city of Phoenix is being faced by extreme heat, but it's much greater extreme heat than even slightly outside the city, just due to quirks of the geography. And so in order to actually adapt to climate change, we need to have very narrow predictions, narrow in terms of space, also narrow in terms of time. And since these systems are so slow to run, it's very difficult to get these kinds of predictions. So what we're working on is AI-based approaches to quickly approximate these simulations. There are several different approaches for this. The first approach that we use is in specifically radiative transfer. And radiative transfer is an especially slow part of standard climate models. It has to do with how energy flows within the atmosphere. Some energy gets reflected back out to space, some energy gets absorbed, some energy gets retransmitted, etc. And we integrate known physics rules about how heat moves within the atmosphere and how radiation moves into these AI-based algorithms, and thereby make them much more reliable and also much more interpretable, so much more sort of convincing to the actual atmospheric scientists. Our approaches have been so effective that they're actually currently being integrated into Canada's global climate model. In our next project, we assume that we have a standard low-resolution climate model. And we try, instead of quickly approximating it, to actually improve the spatial resolution. We take a fuzzy image like this, a standard resolution for reference for climate models. Like, again, these are really slow climate models. So you can see this is a grid around the world. Standard size would be like hundreds of kilometers for a single square. This is why you can't make a prediction if you're the mayor of Phoenix. Several hundred kilometers. That's far too big to actually give actionable recommendations for any particular locality. But anyway, so this is what you can imagine for these like pixel sizes. So you suppose you got this image that's hundreds of kilometers per side on a pixel, and you'd like to make it actually a really sharp image where the resolution is maybe tens of kilometers. Well, how do you do that? You can use AI. You can use AI to enhance the image. This happens all the time in movies. It's actually quite hard to do in practice, but you can use AI to enhance the resolution of images. And we've designed specific methods for doing this that actually, again, integrate knowledge about the physics of the atmosphere or the climate system, respecting conservation of energy, conservation of mass, other physical laws. And we've also used new methods from AI called Fourier neural operators, which actually mean that we can go not just from one resolution to double the resolution, we can actually go up arbitrarily high resolution. You can take a blurry image and you can say, okay, well, I want to dial up the resolution by 2. I want to dial up the resolution by 10. I want to dial up the resolution by 100. And it can do all of these things on the fly without having been designed specifically to do that resolution. And then the final project that we're working on in this space is on climate model emulation. So instead of emulating a piece of a climate model, instead of increasing the sharpness and resolution of the image, you're trying to emulate the entire thing. And this is really difficult to do because there are just so many variables involved. And so what we're actually doing is we're identifying causal relationships between different input variables using causal inference techniques from AI. We're picking out these causal relationships, like this part of the climate system is actually influencing this other part. Some of these causal relationships are known, some of them aren't known within the climate science community. We're trying to identify these relationships and use them to simplify the emulation of the climate system. This also makes it more interpretable and actually more useful to climate scientists who are still trying to identify some of these causal connections. And here is a publication where we actually just make a lot of data available take that data from the climate science community, make it available for the machine learning community, and show that if you incorporate all these different data sources, many different climate change scenarios, you actually get very strong machine learning models. And then the final example that I want to touch on in this sort of in-depth analysis is accelerating scientific discovery. And here we've worked on catalysts specifically. So the energy transition requires efficient electrocatalysts. These are chemicals that can speed up a system. That's what a catalyst does. And an electrocatalyst is one which does so if you add electricity to the system. And in this case, what we would like to do is, for example, produce green hydrogen from renewable energy sources, low carbon energy sources, or other electrofuels, ways to store electricity as a fuel. Traditionally, finding new catalysts requires very slow quantum chemistry simulations. And so just even evaluating a particular catalyst's effectiveness is very slow. Furthermore, there are many possibilities to choose from. There are lots of different chemicals and materials out there, and how do you pick the right one? So both of these are actually areas where AI can help. We're developing AI methods to first quickly evaluate candidate catalysts, take a material and work out how effective it is in a particular reaction, say turning water into hydrogen with the addition of electricity, and simulate the chemistry just much faster than the traditional quantum chemistry methods. We're doing this using graph neural networks, and in particular, very lightweight graph neural networks that allow us to do this much faster. You can see these publications for more details. And then the second piece is suggesting possible materials, right? Because there are many possible materials to try, and it's not just good enough to evaluate them fast. You also have to select good candidates because there are so many. How do you even pick? And so we're doing both of these in tandem, and we're using models called G-flow nets to suggest promising candidate materials. Now, this is not a replacement for scientific experimentation, and it still takes time, but it hopefully reduces significantly the number of experiments that you have to try in practice. Now, there's a question in the chat. Can you touch upon forecasting electricity demand and supply and how AI can optimize that? An overview would be amazing. Yeah, so let's go into forecasting electricity supply. This is often called nowcasting, and typically people will do this for variable sources of electricity, so sources of electricity that are not controllable by people, right? If you're working with fossil fuels, it's typically controllable. If you're working with pumped hydro, that's controllable. If you're working, so it's not just fossil fuels. It's also some renewable sources like hydro. But if you're working with solar and wind, that's variable. And so you need to forecast how much the sun will be shining or how much the wind will be blowing. And so typically people will work with a mixture of time series data, and they will also work with images of the weather. So they'll try to be forecasting what's going to happen in the next few minutes or the next few hours. And they will be using maps of where the clouds are and maps of wind speed. And they will be forecasting this on a very narrow kind of weather forecast. And then they'll use those predictions to guide energy trading markets or to guide decisions by grid operators. And then electricity demand can also use time series data. It could also incorporate other streams of data if there are different kinds of things which you think will be shaping electricity demand. So for example, the temperature shapes electricity demand because people turn on air conditioners if it's hotter. Right? So these are the kinds of data which people will be throwing in, and there are many different technologies within AI for working with time series data to forecast what's going to happen. The most simple ones that are typically used within deep learning are LSTMs, and you might be using transformers now. You might be using a whole bunch of other methods. I'd be happy to talk about this offline, and you can go to the Tackling Climate Change with Machine Learning paper or other papers to find the latest research. There's another question. Would you please be able to elaborate on why AI has difficulty increasing the emulation of images? I'm not sure quite what you mean by increasing the emulation of images. Do you mean increasing the resolution? Why is it difficult to increase the resolution? Well, I mean, suppose I ask you to increase the resolution of an image. It would be quite hard to do so. You could sort of smooth it out, but that would make everything more blurry. If you want to have sharp lines like this line, this is actually very challenging. It's very easy to take this image, which looks very choppy, and just blur it out, but that's not actually gonna help you very much. Often there are fine scale features which you want to really pick out. So that's the kind of challenge that you face in coming up with algorithms for this, and why AI is useful more than simple approaches like bicubic interpolation. A particular challenge that we have, why is there a challenge in downscaling by 10 times or something like that? Where does the information come from? Yeah, really great question. So a very quick 30-second introduction to Fourier neural operators. Fourier neural operators are a way to treat discrete objects like continuous objects. A Fourier neural operator doesn't work on backing up. If you think of an image, that image is discrete pixels. It's individual pixels, but it's representing some real thing in the world. And that real thing in the world doesn't have pixels. If you have 1,000 by 1,000 image, it's not like you looked, and that's an image of a person. It's not like you looked at their face. You would find it dissected into pixels. The face is a continuous object. And so the image is a discretization of a continuous object. In the Fourier neural operator framework, you think of an image as a discretization of a function. That function is a continuous object, and you can discretize it at any resolution that you want. With Fourier neural operators, you can take an image, turn it into a function, and then do a transformation on the function instead of doing a transformation on the image. Since you've done a transformation on the function, you are able to then discretize it to whatever resolution you want. And so what we do in our super resolution approach, our downscaling approach, is we take an image, we turn it into a function, we process that with a Fourier neural operator, and then we discretize it to whatever resolution we want. It's not guaranteed to be correct at any resolution, but at least it has reasonable properties, and it's actually much better than even specialized algorithms trained on that resolution. If you suppose you have an original image, and then you have, and then you're trying to increase the resolution by a factor of 2, and then you're trying to increase the resolution by a factor of 4. If you use our approach, trained on increasing the resolution by a factor of 2, it beats all the other algorithms at that task. But it also beats the algorithms that were trained to increase resolution by a factor of 4, even though our algorithm wasn't designed to do that. So it can zero-shot generalize to higher resolutions. And that's because using this Fourier neural operator framework of treating things as images as functions, it actually is working within, in some sense, the right basis for images, which is continuous rather than discrete. I hope that helps somewhat. I'm happy to talk about it more offline. If you didn't understand that, that's completely fine. It was a really, really fast introduction to something that's actually really complex, state-of-the-art machine learning. Okay, let's move on to some broader considerations on the whole field. And then we'll get into the policy space and like what we should be thinking about in terms of actually facilitating work in this area. So the first key consideration is machine learning and AI are not some silver bullet that's magically going to solve climate change. You can see in all of these contexts that you really have to tailor the AI approach to a particular challenge within a relevant domain of application. It's not like they are creating whole new families of climate solution. They're really helping address bottlenecks that existed already, and they're only relevant sometimes. The high impact applications of AI that we're seeing here are also not necessarily flashy. You hear about AI in the news in contexts like self-driving cars and ChatGPT. Those are probably both going to make climate change worse, as we'll see in a bit. Oftentimes, the most impactful applications of AI are very prosaic, like predictive maintenance of railroads, working out where there's going to be a failure in a rail line. That's actually a really interesting and challenging AI problem, and it's being used extensively. AI is being used extensively for this particular problem by Deutsche Bahn and other railway operators. So it's already out there, but it doesn't get a lot of press because it doesn't sound as flashy. So this is something that we're contending with. People don't even necessarily realize the ways that AI is being used around them in ways that are aligned with climate action, as well as other ways. Fundamentally, everything here requires interdisciplinary and multi-stakeholder collaboration. It is so easy for somebody from tech and AI to come in and think that they know what they're talking about and go in and try to solve somebody else's problems. And if you do that, then you fail, and you often make the situation worse by distracting people from lower tech ways of solving something. It's necessary to work together with multi-stakeholder groups in order to scope the right problems, make sure you're solving a problem that is actually useful and well-matched to your tools. It's necessary to incorporate relevant domain information. We saw throughout here, every algorithm that we were working on, it requires some integration of system physics or engineering constraints or knowledge of ecology. Integrating this kind of information is really key in every application. And then finally, shaping pathways to impact, right? Ultimately, the goal of work in this area is not to write a paper that gets published in NeurIPS, or even create a startup that has a lot of investment. It's to help address climate change. And making a successful business or writing a paper is great, but those are ways to achieve the ultimate impact. And making sure that one does have a pathway to impactful deployment is really essential, and integrating multiple stakeholders from the start is part of that. So it's really essential for research projects to bring in researchers from multiple areas, but also the people who are going to be developing and deploying those approaches long-term, whether those are people from the private sector, from established companies, entrepreneurs and investors, or public sector entities, because sometimes the deployment pathways go through the public sector. Equity considerations are also key. Several different families of equity considerations. AI is not known for being a field that is extremely equitable from a range of perspectives. And I say this as a cishet white guy at one of the traditional centers for power of AI in the world. There is huge disenfranchisement of most of the world when it comes to access to AI tools, and the infrastructure needed to work with them, data and computational tools, to say nothing of funding. And so there's a fundamental need to empower diverse stakeholders in this space, and in particular in AI for climate, because climate change is a global problem, remember, that affects different populations and different communities differently. It is essential, both from a perspective of equity and from the perspective of practical change, that diverse stakeholders be included in the solutions. It's necessary in selecting and prioritizing problems. We see a ton of investment and attention given to problems like wildfires. Wildfires are a major problem, and they are definitely worthy of attention in terms of VC funding, in terms of research. However, I would like to see the same amount of VC funding and research being directed at problems like locust outbreaks and melting glaciers. These are also exacerbated by climate change. The only difference is that locusts and melting glaciers affect the global south primarily, while wildfires primarily affect the global north. And there is a correlation in what gets the most attention. Ideally, all these problems will get attention since they are all worthy of being addressed. And then ensuring that data is representative. Remember, machine learning requires data. And if your data comes from certain countries more than others, then your algorithms will work better for those countries rather than others. Unless you really, really work hard, you are going to have data imbalances and you're going to have data and algorithmic inequities. The flip side, though, can also be true. Sometimes you have imbalanced data not from extremely well-resourced countries. Sometimes you have the most data from countries that have the least data regulation. That could be countries outside the EU, for example. Maybe the EU has regulated personal data very effectively. And so it's impossible to collect various forms of data. So you instead go to an under-resourced country or a country with lax data regulation and steal personal data from people because there isn't a law against it. This kind of data colonialism can lead to data imbalances the other way. So thinking about all these kinds of inequities is really important. Now, I'm a researcher in computer science. One of the reasons I think that this space is really interesting is because it poses challenges for researchers. It is not simply a question of taking AI tools out of the box and using them immediately. Sometimes that works. And there is, to be honest, a lot of low-hanging fruit there. There are thousands of startups that need to be made and thousands of businesses that should be integrating existing AI into their business models. But there's also room for huge improvement in what we have. We have many common challenges across machine learning for climate relevant applications. We see constraints on variables like physics and engineering constraints, like we've seen today. Those are really common, and it's very hard from a methodological perspective sometimes to integrate physics and engineering into your machine learning system. Distribution shift. Shift across geographies. You're trying to generalize across different geographies. How do you do that if there are data imbalances? Time, generalization across time. The climate is changing. What are you going to do if all your data comes from historical data, but you have different data now that weather and climate patterns are different? That's another interesting challenge for machine learning methodologies. Limited or imbalanced data. Data is generally really limited, and it's often very imbalanced. How do you work with such considerations? And then interpretability or accessibility, because if you are going to make your algorithms be useful, you're going to have to make them be generally at least somewhat transparent in how they work. These are common challenges, and the forms that they take are often very domain specific. You often end up with very specialized challenges for the particular problem in question. And this runs against the general paradigm of machine learning, which is to use high-powered general techniques that are designed for a wide range of problems. But in many climate-relevant applications, these fail catastrophically. People use the latest vision transformer for satellite imagery, and they find that it actually performs less well than random forests. We find this. It's a common kind of challenge. And that's because these techniques were not designed for these applications. And often they weren't designed for any applications. They were designed for some toy data set that actually doesn't have connection to what people need in real life. And there's an innovation needed in structures for incorporating domain information and not trying to learn everything from some abstract general purpose data set that actually isn't necessarily useful for any particular task. Let's look at an example of how the paradigm for innovation in AI and machine learning has significant issues. Here, we're going to look at ImageNet. ImageNet is one of the major data sets used for developing computer vision algorithms, so algorithms for processing images. It's used for developing these algorithms, so designing the algorithms. It's also used to pre-train them, so as a first data set that you use to fit your algorithm when you're trying to do a vision-related task. And there are many issues with ImageNet. People have criticized it for many kinds of problems, such as extreme misogynistic biases and racial biases. And many of these problems arise from the fact that such benchmarks like ImageNet were designed by computer scientists from data scraped from the internet in great and messy abundance. In our case, we're going to analyze it from the perspective of ecology, and that's because 27% of ImageNet is actually wild animals. So how is it actually designed to be appropriate for identification of wild animals? The goal here is to identify a species of animal from an image. So how good is the data set at capturing this challenge? Well, we worked with ecologists. We found that 12% of the images are flat out wrong. They're not showing the relevant animal. 12% of the categories are contradictory. This is on top of the 12% of the images that are wrong. The categories are contradictory. So for example, there is a category called meerkat, which is a kind of mongoose, but there's also a category called mongoose. And most of the images of mongooses are actually meerkats. So what do you do if you're the algorithm? Well, there's huge ambiguity. The species are heavily biased towards the United States, somewhat less biased towards Europe. For example, in classification of birds, there are 50 species of birds called jays. This is a blue jay, this is a green jay, this is a Eurasian jay, and this is a Sichuan jay. This one is found in Canada and the US. This one is found in Mexico. This one is found in Europe and Northern Asia. And this one is found in China. Can you guess which out of these 4 species is primarily represented in the dataset? So right, it's the one in the US. It's only found in the US and Canada, and yet it represents 2/3 of all the data in the dataset. And there are, remember, 50 other species of birds which are jays, but the jay class is basically just this one. This is indicative of the kinds of issues which exist across machine learning. The data was collected without the relevant people in the room, so there's huge inaccuracies in it. 12% plus another 12% being wrong, that's enormous. This is a data set where people publish papers on the basis of 0.5% improvements. And here we have a quarter of the data being flat out wrong. Then these biases are really insidious because this is a data set that people use to train classifiers for wildlife classification. I remember giving a talk on this paper to some computer scientists in Spain, and one of them said, "Oh no, I just trained an algorithm to classify species in national parks in Spain using ImageNet. But all the data is from the US." So this is exemplary of ML innovations developed without the stakeholders who are relevant to actual societal impact. So we need a remodeling of how we do AI and ML innovation. Now, I think it's time to have a note on GPT and other generative language models, because I often get a lot of questions about this. None of the algorithms that I've talked about in this talk so far have to do with GPT or other generative language models. And this is not because I'm prejudiced against those algorithms. They're just not really useful in this kind of context. So why is that? Well, generative language models are now being proposed as an answer to virtually everything. And I think that part of the reason why that's the case is because they've gotten a lot of visibility, and many people aren't familiar with other AI algorithms. This is the first time that many people have seen any kind of AI, or at least that they're aware of. They don't realize that AI is being used in Google Translate, and it wasn't GPT. That AI is being used in image search, and it wasn't GPT. That AI is being used to select the ads that they look at and the stocks that they trade. That is also not GPT. And so all of these other approaches maybe have limited visibility because they're not as flashy and user-friendly. Excuse me. One moment, I need to get a glass of water. Sorry, thanks for your patience. For specific tasks, generative language models can absolutely be in particular, accessible tools. They're very accessible to users who don't necessarily have the ability to program. But it's worth noting that these are really only in the domain of language and text, not in other kinds of data domains. And even outside natural language processing, they're generally not applicable at all. But even within text, there are specialized tools which are generally much better at specific tasks. So if your goal is to search through the web or to search through a database, there are generally better algorithms than generative language models. Because generative language models, it's there in their name, they're generative. They're not trying to pick out information. They're trying to synthesize stuff that sounds right. They're predicting the next word. And that is not on the basis of truth. It's on the basis of what sounds right. So they're very good at making content sound right, but they're not good at actually finding reliable content or coming up with conclusions. They're coming up with ways to present that content. So if you're trying to make existing content more user-friendly, they're a very good tool for the job. But oftentimes there are very specialized tools which are actually much better at doing something. So I get really scared if people talk about, oh, we're going to replace Google search by large language models. Google search is much better than large language models at actually searching. And in some cases, using these kinds of algorithms is actually dangerous and can have serious impacts. It's worth noting that people talk about hallucinations or fabrications, so false statements made by large language models. This is the systemic flaw. They're not designed to be truthful. They're designed to sound good. There's no real way around this until we come up with a completely different kind of algorithm. The way that they are designed is to sound good. And so sometimes that's what you want, but sometimes that, generally speaking, that isn't what you want. And so this is worth bearing in mind that they are a useful tool for specific things, but they've kind of been overhyped to many different contexts where there are better AI tools already out there. So I want to also spend a little bit of time thinking about how AI can negatively impact the climate. There are many different ways that AI is being used across society, and its impacts on climate change aren't just positive ones. The kind of impacts that get a lot of press here are computation. So AI requires computers, computers use energy, computers also use water, they use heavy metals and other materials, so there are embodied emissions as well and other environmental impacts. This is very true. And it's worth noting that these are potentially very significant, but they are actually low for most algorithms. Most of the algorithms that my team uses could run on a laptop. But if you're looking at something like a large language model or some other big models, those can be enormous. It's just like AI is a very catch-all term. It refers to the computational equivalence of elephants and also the computational equivalence of mice. So it's worth remembering that this is a very variable kind of impact. However, the biggest impacts of AI in negatively impacting climate change are actually not from computation at all. AI is a hammer, and what you're hammering often matters much more than how the hammer was made. And so just like AI can be used to help in applications that are positive for the climate, it can also be used for the opposite. AI is used extensively to accelerate fossil fuel exploration and extraction, leading to up to a 5% production boost, which is huge. It's been estimated that the impact overall of AI and advanced analytics is $500 billion in additional profit for the oil and gas industry just by 2025. So these are very, very major applications. And then there are systemic impacts. AI is being used pretty much universally across automated advertising systems. All of online advertising relies on AI now, and those systems are designed to increase consumption. These are explicitly designed in areas like fast fashion to accelerate the consumption of energy and resources. And so we're seeing vast impacts from AI that are just very poorly quantified. And increasingly, as we're seeing tools like GPT coming online, they are very easy to use for misinformation It's always far easier to create misinformation at scale than it is to create real information, regardless of what you're doing. So I'm really worried about these kinds of systemic impacts. It's worth noting also that many of these impacts really depend upon how we use a technology. It's not inevitable how a particular algorithm or a set of technologies gets used. By way of example, think about autonomous vehicles. So autonomous vehicle technology has gotten very popular in terms of self-driving cars. But self-driving cars are actually expected to make climate change worse because they will decrease the barrier to driving and result in people driving more, even if each mile driven becomes a little bit more efficient. On the other hand, autonomous vehicle technology, the same technology, can be used for buses or for various kinds of freight transport in ways that could make climate change better. But the implicit priorities and the implicit decisions made by the technology industries working on these problems are leading us to a certain kind of societal impact. So it's important to remember, AI for good is this label that gets flung around, and it often is used to mean, let's use AI for this specialized application that seems good. But actually, it should mean shaping all applications of AI to be better for society. If we have autonomous vehicle technology, great. Let's work out how to make it most impactful for society in ways that we want. Autonomous buses are also a great company. They're also very profitable. Why aren't we working on those as much or more than autonomous personal vehicles? And we should think critically about the choices that we make as a society and as individuals within this space. The final thing that I want to touch on here is policy implications. And so here I'm going to be summarizing a report that we wrote for the Global Partnership on AI, which is the OECD's organization for shaping national and international AI policy, and how to steer government actions specifically to facilitate AI in the context of climate action. And the first part of the report that I want to highlight is that there is a need for facilitating AI with a responsible AI lens in the context of climate change. There are a lot of words that get shared, that get thrown around with respect to responsible AI. You may have heard words like fairness, accountability, safety, privacy, security, robustness. It's worth noting that these words can mean very specific things in different contexts. And in particular, in a climate context, they can actually mean very different things to what people in AI and tech normally mean. So for example, robustness. Robustness in machine learning is typically a very specific notion of, suppose an adversary comes in and does the worst possible thing. Is your algorithm going to still perform well? Robustness in the context of power systems may be very different. It may be, suppose that you have some outages on your power grid. They're not designed to be malicious. This is just, system failure. How well is your algorithm going to perform in this context? Very different notion. Maybe there's a notion of Lyapunov stability, where you want your algorithm to be stable under certain kinds of perturbations. Again, a different notion of robustness. Safety may mean a very different thing when we're talking about systems that are very critical to national or international operations, like power generation or like transportation, manufacture of security critical materials. These kinds of themes take specific forms in climate relevant context. There's a need for holistic climate impact assessment. I'll get into that a little bit more in a subsequent slide, but it basically just means thinking about the impacts of AI algorithms holistically on the climate. There's a need for an equity and climate justice lens. There are frameworks of climate equity and climate justice that have to do with analyzing the way in which both climate change and climate action disproportionately benefit and disadvantage certain populations and individuals. And thinking about AI action from the perspective of climate equity and climate justice is really important. As an example of the points that I was highlighting before about inequity in the the kinds of problems that get prioritized, many companies in Silicon Valley are focusing on wildfires. Not surprisingly, wildfires affect Silicon Valley and all the investors in Silicon Valley. Kuzi, which is a tool by a Kenyan company, a leading agriculture company based in Kenya, uses AI instead to predict locust outbreaks. This is a problem of relevance to Kenya and more broadly to East Africa and the Middle East. You can go to the full report for a number of these use cases, which are designed to feature different global contexts, different kinds of algorithms, different kinds of applications. But it's really important to remember that the climate justice lens should impact the way in which we prioritize different applications and different stakeholder groups. And then multi-stakeholder engagement is really, really key here. Governments should establish and implement standards or best practices guiding the responsible practice and, importantly, the participatory design of AI in climate contexts. Often AI is not designed with a multi-stakeholder framework, with a participatory design framework. Data and digital infrastructure. AI requires data, and it requires large amounts of computation, or at least moderate amounts of computation. And access to this kind of infrastructure is not necessarily always available for anyone. Some considerations. The relevant data may not exist at all. It's possible nobody collected it. Maybe it's unequally distributed across different geographies, across different stakeholder groups. Maybe the data is privately held and not available publicly. Maybe different companies would love to have pooled data, but each one of them has their own siloed data pool, so none of them can actually do very much because there's no large data pool. There are often very poor standards for data sharing. There may not be incentives to do so, but there also may not be standard formats or requirements on data provenance or data quality. And so there may not be vehicles for people to share data effectively. Sorry, I already mentioned this. And then computing infrastructure is also often a bottleneck. We may jump to thinking of, oh, countries in the global south have very limited computing infrastructure. This is often true. Countries in the global north also often have very limited computing infrastructure. Our partners in the Canadian government generally don't have access to GPUs for running these machine learning algorithms. There is often a disconnect between what is available in academia and the tech industry and what is available in public entities and in private entities that aren't part of the tech industry. And people can have huge computing bills if they're always going to like Amazon or Google for cloud services. This is not a scalable option. So what can governments do? I'll gloss over this case study. Some selected recommendations: establishing data task forces and platforms to facilitate data collection, standards, and sharing in climate critical sectors. These are going to be different challenges in different sectors, but having a power systems data task force, really essential. Support the availability of compute and data storage for researchers, civil society, and smaller scale enterprises, because oftentimes there really aren't very many options for somebody who wants to implement even a relatively lightweight AI algorithm. Computationally, and in terms of, again, data storage. I'll get into some more recommendations related to this in just a moment. Research and innovation funding. The funding landscape is highly imperfect in technology, and specifically in AI. There is extensive funding for it, but it's often focused on methodological innovation, not on impact-driven innovation. And these can lead to different outcomes. Making the coolest new algorithm that leads to some imagined form of, some progress towards some imagined AI utopia is very different to innovation that's guided by a particular application that you can point to. They're both important forms of innovation. We need both of them. But oftentimes one gets prioritized instead of the other. Climate relevant funding is often both very limited and often sector specific. And people in climate relevant funding streams often don't have the relevant expertise to assess new technologies. And so we end up with very flashy AI getting funded, but not the AI that's necessarily going to actually make a difference in that sector. There's a lack of prioritization, potential neglect of less flashy, low-hanging fruit. There's also imbalanced funding geographically, of course, and the priorities are, again, often driven by the global north. Some recommendations in this space. First, to ensure support for AI projects includes impact-driven funding. It's not just methods-driven. And it includes consideration of pathways to deployment. Ensure that there is capacity for expert evaluation of multidisciplinary projects across funding streams. And developing and prioritizing key grand challenges for AI and climate change, like, for example, AI in materials discovery, or AI in carbon stock estimation, etc. Now, I'll note, I talked about funding streams here. I'm talking about the research landscape, but I'm also talking about the entrepreneurship landscape. I'm also talking about the broader funding landscape here. Oftentimes, one thinks of government funding as being, in the AI space for research, but there are so many other ways that money gets distributed by public entities and also by private entities. This was a report for governments, but the same principles would apply to VCs. Deployment and systems integration. There is often a gap between what is being developed in the research space and what gets turned into effective companies. Now, how do we fill that gap? There's a need for smart money to accelerate commercialization, which is really well scoped to the particular challenges and capabilities of the systems that we're talking about here. There's a need to understand incentive structures. Many, probably most of the applications that I talked about are well scoped for scaling and deployment by the private sector, but not all of them. Some of them fall outside traditional incentive structures and should be considered as maybe public benefit applications, applications which are sponsored by national or international government. And across all of these different kinds of deployment organizations, there are often bottlenecks in organizational culture and infrastructure that can slow adoption. We see, for example, that in heavy industry, oftentimes, steel manufacturers, or outside of heavy industry in power system settings, in power grid control, there are understandable concerns about integration of new technologies because they could be dangerous. They could lead to system failure. This is not wrong, but it does mean that certain areas are very slow to adopt new technologies, and there's a need for specific work on ensuring that technological progress and tools are available and well tailored to the needs of such stakeholders. And so how does one, one of the critical points here is reliability and security guarantees. Those can be needed in many such contexts. So how do we do this? We recommend the development of cross-sectoral and multi-stakeholder innovation centers, which can help incubate projects and facilitate collaborations, ensuring that they are driven by deployment-centered metrics for success. So that you are building something that's actually designed for the people who will use it. And by way of example, here is a challenge that was recently released by a whole coalition of power system operators, France's RTE, and a number of others. And this was a really great example of people outside of AI recognizing that they wanted to consider AI solutions, but they needed to ensure that the solutions were being built for their use cases. And so the power operators came together and they designed a challenge with data and with metrics based upon what they would need if they wanted to actually integrate these algorithms into their own systems. And they said, okay, can you solve this? It's a really hard challenge. Use reinforcement learning to control a power network. It's still running, but it's been really effective, not just at getting researchers interested in this space. There's a prize, there are incentives as publicity, but also in ensuring that that work is actually grounded in what people need, right? Because the challenge was designed by the power system operators. You can bet that if people solve it, they will actually have created a solution that will be immediately scaled around the world. So this is the kind of thing I want to see more. And there's a need in situations where, in power system operation, there are clear pathway to commercialization. But in other contexts, there is a need for development and maintenance of non-commercial public interest applications. So a great example of this is Climate Trace, which is a coalition of companies that are backed by philanthropic and government funding, which is working to monitor all the carbon emissions around the world using AI-based approaches and other approaches. And that's because we need a better system of accounting and holding people accountable, holding entities accountable for emissions. Reducing AI's negative impacts on the climate. We've seen that AI can be used positively for climate action. There are applications that increase emissions, there are system-level impacts, and there are emissions from computation and hardware. And here, the important thing to understand is that climate change needs to be a central consideration for all AI-enabled technologies, not just explicitly AI for good applications. And there's a need for reporting of life cycle emissions associated with the development and use of AI. That's not just the computation of the algorithm, it's also what it's being used for. It's also estimates of how it's impacting society more broadly. Some of these will be qualitative assessments, but it's really essential that we have this information coming on a holistic impact assessment. And then finally, I want to touch on capacity building. It's necessary to support capacity in AI for climate, because this is an intersectional area that where talent is very limited. Capacity is needed across a wide range of entities and geographies, government, private sector, civil society, and there's a need for cross-functional, cross-sectoral coordination. There are huge risks associated with limited capacity. For example, many entities currently do not have the ability to do AI in-house. And so they're increasingly reliant upon consulting organizations that can, for example, lead to very high costs, or system capture where over-reliance upon a particular entity could lead to critical failure of many different stakeholders, or over dependency and overfitting to what one particular entity can provide. I know that, for example, a large number of stakeholders surveyed in Germany, I believe, said that if they needed AI expertise, they would turn to Google. These are, traditionally, Germany actually hates Google. So it's really interesting to see that in many cases, the stakeholders who need AI expertise don't know where to go. They don't realize that there are a host of specialized small solutions providers, companies that are focused on AI for steel or AI for agriculture, etc., that are much better equipped than the big tech companies to provide these kinds of services. But there's a knowledge gap in bringing together the stakeholders who need AI capacity with the people who actually have that capacity. So there's a need for various kinds of programs here. There's a need for AI literacy across different entities. Upskilling programs for governments, climate-relevant industries, civil society. What is AI? How do I use it, roughly speaking? How do I know when it's relevant? Who do I talk to? And there's a need for bringing AI experts into climate-relevant sectors. So we don't just have generic tech people who have no idea how to work in these different areas. There's a need to support trusted AI for climate solutions providers. This ecosystem, which we really want to create, of small-scale, very focused solutions providers, maybe focused on regional challenges, focused on sector-specific challenges, that can help bridge these gaps between tech and between deployment. Whew. I've talked for a really long time, and my voice is pretty much shot. In closing, I want to leave you with pointers to more resources. This is Climate Change AI, which, as Michael said, is a nonprofit which works on catalyzing impactful work at the intersection of climate change and AI. We have reports aimed at researchers, practitioners, policymakers, including that GPay report and the policy report, and also the Tackling Climate Change with Machine Learning report and others. We host events. Our next workshop is going to be at NeurIPS in December of just a couple of weeks, actually, in New Orleans. That is open to the public and is going to be live streamed for free on our website. You can look at past papers. There are about 600 papers there currently. all peer-reviewed, the forefront of the field on our website. These are just the papers from our own events. And we host a summer school, which drew about 10,000 people last year in its virtual form. There's also an in-person component, which is a bit more competitive. And we're going to be running it again so stay tuned for applications for that. It's open not just to students, it's intended to be also for people outside of academia. A large fraction of the people taking it were entrepreneurs or people from the public sector, et cetera. We also have our own grants program. So stay tuned if you're a researcher for the next announcement on that, which will open in just a couple of months, probably. We've so far given away, I think, actually about $3 million in innovation grants. We have a newsletter, which if you sign up for one thing, I would recommend signing up for that. It gives a monthly update on everything that's going on in the space of climate change and AI. We also have other community resources and regular webinars and Happy House. Thank you so much for listening. And thank you also to my research group who made all of the research that I talked about previously possible. We are hiring, so if you are interested in positions, please do reach out. Thank you so much, and I look forward to a few minutes of questions.
David, that was excellent. I can't think of a better presentation that really brings together a lot of the seminar series topics that we've learned in the past year or so. Clearly there's this need for responsible AI, and that we need to be critical about how we're using AI and how we're actually benefiting society. Clearly, we need more financial accounting disclosure and how we can show ESG-related information in a meaningful way. We need to think about performance measurement and how we can create impact measures. And I think one thing that I really want to highlight, I am cognizant of time, is that what David said really holds true, in that we all have a role to play, right? Everything that David talked about was really about collaboration. Regardless of what your expertise is in, I think there is a fundamental role that you could play if you're interested in this space. So given the time, David, we won't open it up for Q&A. Just wanted to thank you again. And I wanted to thank everybody on the call who has been part of this seminar series since inception. I want to wish everybody a wonderful holiday season, a safe and relaxing holiday season, and we will see everybody in January. With that said, thank you again to David. Thank you to all of you, and I look forward to seeing you in the new year.
Thank you so much for having me. Take care, everybody.